All right, hey guys. Our first part of this training session is about ROS. And hello, can you see me, guys?
Yeah, I can see you just fine.
All right, great. Hi. So our first part of this training session is about ROS, and I recorded a video about a kind of a brief introduction about how to use ROS to control our robots. My demonstration is on CR3, which is just beside me. And this ROS training session is meant to be a pretty um, easy one. If you are never used ROS before, this is the right thing for you. And if you are got some experience in ROS, so just check our CR ROS or other check our GitHub, and there will be a lot of manuals and README files you can check out. All right, so I will start the video now.
Same as computer.
All right.
Looks like the sound will. I think there's a setting it's called same as computer.
Like
Or the same as system.
So guys, if you can hear the video now, you can type 1 in the chat. Okay. All right. Give me a few seconds. I'll try to fix it. All right, let's just leave the audio away, and I will do introduction again. Okay. So, okay. So you can see the screen, right? Okay. So welcome to Java application training session. I am Hal, your tutorial on ROS today. Today we're going to talk about ROS. So ROS stands for Robot Operating System. It's a open source OS for all kinds of robots. And basically you can control robotic arms or robotic cars and UAVs, all kinds of things. All right. So it's a powerful tool, and it has a lot of functions like hardware abstraction, low-level device control, and ROS also implemented some commonly used functionality, and it can pass message from a different process. Also, ROS runs on Ubuntu, so you have a package management tool. So the most important tool in your journey will be ROS Wiki. ROS Wiki provides a whole list of documentations and tutorials that you can check on. And I have to say here that learning ROS is quite a long-term work, and today's tutorial will only be the first step of everything. And you can see, basically, you will need to go through all these tutorials. I think the basic level is quite enough. Intermediate level will be a more high level thing, and using Drupal device will not be that hard. Well, our APIs are quite easy. And okay, so ROS has a lot of distributions. For every few years, ROS will release a new version for a new version of Ubuntu. So every different distributions of ROS runs on different version of Ubuntu. So the latest version of ROS is ROS Noetic, which runs on Ubuntu 20.04. And if you download a wrong version of ROS onto your Ubuntu, the download will just fail. So you won't successfully install a wrong version on your Ubuntu. So I don't like that. And currently, our Drupal device supports 3 ROS distributions, which is the latest Noetic, and ROS Melodic, which is the older version, runs on Ubuntu 18.04, and ROS Kinetic, which is already end of life. So I won't recommend you to use ROS Kinetic, but we still support it. It runs on Ubuntu 16.04. And for this demonstration, our ROS version will be Noetic. Okay, the newest version. So ROS installation. In ROS Wiki, you'll see the install right here. So when you click inside, it will let you choose which version would you like to install. And for now, we will just choose Noetic. So then choose Ubuntu, which is what we are currently using. And if you want to install ROS, you just follow all these steps. Just copy and paste all these commands into your Ubuntu terminal, and basically the installation will just success. Install an older version like Melodic or Kinetic will be kind of tricky because you have to type all these. You're gonna go through all these steps. But for Noetic, there is a easy way for you. So you can see. Oh, sorry, there's a annoying ads. I'll just. All right. So you can see this ROS one-line installation. So if you are installing Noetic, just click into this one-line installation and copy this line into your terminal. Hit enter. The whole process will just go automatically. You can see what I'm doing here. Just copy and paste and hit enter. The process will just go. Okay. So if you want to install ROS Melodic, just do the same thing that I said. Go through all the instructions on that page, on this page, step by step. Don't miss anything, and your installation will be just fine. When your installation when you think your installation is finished, you can run a ROS core on your terminal. And if your install is a success, you will see your ROS distribution and ROS version right here. Okay, so now I've already installed Noetic, so there will be ROS distro Noetic right here. Okay, so after install ROS, we will need some necessary packages to run our control package for our dobots. So the first one is Git. You will need Git to download the robot package from our GitHub. And to install Git, you can see how to install Git right here. You use sudo apt install. Use this command, and it will just automatically install. You will need to input your password for the sudo command. Okay. And the next one is move it. It's kind of one of the most powerful tool in ROS. You can you do motion planning, inverse kinematics, collision checking, all these powerful functions that you can use. So to install move it, you can also check the instruction here. Use sudo apt install ROS dash your ROS distribution dash move it. Okay, so for your ROS distribution, if you're using Noetic, just use this command. If you are using Melodic, type Melodic inside in the middle dash. Okay. So you'll see here, I'm using Noetic, so I'll just use sudo apt install ROS Noetic move it. And you will also need the password for the sudo command. So now this is our GitHub, and we support all kinds of robots we supply. Like for MG400, we have MG400 ROS, and for what I'm using is a CR robot. For M1 Pro Magician, you can find all the kind of things here. So for basically, I'm using CR, so I will need this CR ROS package from here. And you can see it supports basically all kinds of our robots from CR3 to CR16. So to download this this package, we need to go to our workspace, use cd change directory, catkin workspace source, and we will download the CROS package into the source folder. And then we use this git clone command from our GitHub website. And note here, v1.0 is the latest version, which currently support ROS Noetic. And if you're using Kinetic or Melodic, you can change from v1.0 to Melodic or Kinetic. But 1.0 also support Melodic and Kinetic, so just use 1.0 is the newest one. Okay, so now we need to compile this package. We need to go back to catkin workspace. We can use cd catkin workspace or the cd .. which means go back to the upper folder. So now we are in catkin workspace. We type catkin make and enter. The whole of catkin workspace, all the packages inside it will be just automatically compiled. Okay, so now we need to set our robot type, because currently there are 4 different type of robots in the CR ROS. Okay, so for me, I'm using a CR3. So we need this command right here, echo export robot type equal to your robot type, which is CR3 for me, and goes to bash RC. And after change this, we need to activate this change. So we need to source the bash RC, both of these scripts. So these 2 steps are kind of necessary, because if you don't source these 2 bash, the system will not refresh itself, and it won't accept your change on the robot type. And now we go to RViz. RViz is a RViz come with your ROS, so you don't need to download it. So RViz is a visualization tool. You can find all the documentations right here. It's in ROS Wiki, ROS Wiki /RViz, and basically in RViz you can visualize what is the current status of the robot, like how the positions of the joints are, and also if you have installed cameras or other sensors, you can also visualize what is the robot looking at, or how the sensor is detecting the environment. It's a very powerful 3D visualization tool for you if you don't have directly visual contact with your robot. So, and you can see all the documentations and tutorials are all here if you need to learn something about RViz. But now let's use it as a black box, okay? So yeah, you can see this is RViz. There is a joint state publisher. We have just simulated a robot. Okay, we have not connected anything yet. So you can use this simulated robot to test your code and test how the robot is moving, test your motion plan. So it's more safe and convenient than to test on your real robot. So so now we need to run. We want to have a look at what RViz is. If you download the CR-ROS package, you'll be able to see there's a lot of launch files inside it. And now we are doing we are launching a demonstration file, a preset 3D visualization setup. So before we use any ROS command, you will need to source this setup.bash to for every new terminal that you use. Okay, if you don't, the ROS command will not take effect. So when I mean a ROS command, you will see right here, there will be a ROS something. So I'm launching a launch file. So the command is ROS launch. It's a ROS command, so we need to source the setup.bash. So this launch file, displayed launch, it will just initialize RViz and generate a CR robot. Okay, just like what we have demonstrated before. So you can take a look at it. It has all the from joint 1 to joint 6. You can control the angles of each joint right here. Okay, so using RViz individually cannot do anything for your project. So now we have a look at the MoveIt that we just installed. It's a motion plan software. Also, we have a demo for both this launch file. This demo.launch will launch both RViz and MoveIt. So you can have a look right here. All right. So basically, the the GUI is pretty much the same, but you can see there's a little blue ball right here that you can drag. This is the center of your robot end effector flange. So if I drag it somewhere inside the workspace, you can see a orange robot right here. So this is kind of the target position of the robot for this target point. And if you hit plan on the panel on the left, you can see move it just automatically plan a routine for the robot from its current position to the target position. The white robot is the current position, and the orange one is the target position. The moving one is the planned path. Okay, and you see, note that the white one has not changed because we only planned this path, but we have not executed. The robot didn't move. So this process is for you to check if this path is really safe for your real environments, because you haven't input any like obstacles around the robot inside this simulated area. Okay, so you can use this plan to check if this motion is really safe, and you can then hit execute. Yeah, you just check if the environment is safe, and if you hit execute, the real robot will just move. So here you can see that the white one indicates the represents the real robots. But although this demo is simulated, we haven't connected anything yet, but you just know what I mean. Okay. All right. So now we can connect our robot right now. So Double Control provides a basically a TCP interface from your Ubuntu PC, or you are using a virtual machine. It's also okay. I'm using a virtual machine. It built a TCP connection from your PC to the robot. So before you build this connection, you can modify two parameters. It's right here. gedit is the original text editing tool for Ubuntu, so we just use this. We need to modify the bringup.launch. Just type this command, and you see there are we need to have a look at these two parameters. Join publish rate. This is how fast your robot publishes its current join status to ROS. So the higher rate it is, ROS will know better where your robot is really at, and the planned motion will be more close to your actual movement. Okay, so this unit right here, this 10 right here, the unit is hertz. So basically it means that it sends the robot drawing state 100 times per second, and yeah. And the second parameter here is trajectory duration. This is how fast ROS, or we say move it, send a move it point to your robots. So this is a two-way connection. Okay. So this is how fast move it send a new point to your robot. For here, 0.3 is second. So for every 0.3 second, move it or ROS will send a new point to your robot to control it to move through the planned path. So if you feel your robot is like moving like little and little and little and little, which means your this time interval is a little bit too large. You will need to reduce it to like 0.1 or something. Also, the fast this rate is, the higher CPU usage will use. Okay, everything has a price. Okay, so now you will need to change your internet connection settings, as you will change this when you connect to your Drupal Studio or other Drupal SC Studio or TCP interface when you're not using ROS. Okay, so for CR, this IP should be one. If you are using wire connection, it will be 192.168.5.1, the 5. Something else, not the one, something else. Okay, because the default IP is .5.1. Okay, so if you are using, you need to change in Windows if you are using a virtual machine. But if you are using a dual system or simply a Ubuntu computer, you can modify it in your Ubuntu system over here. I'm using a virtual machine, so this page it's just meaningless. Okay. So basically change the website, the internet settings in your Windows if you are using virtual machine, and change this setting in Ubuntu if you are using dual system. Now you can build the connection. Use bring up launch and type your robot IP. Note that you shouldn't type any space between the robot IP and this the numbers. So you will see here connected successfully, which means that you have already built connection between your PC and your robot. If this 3 connections successfully didn't show up, something goes wrong. Maybe your robot didn't boot up successfully, or there's something wrong with your internet settings. And so we leave this terminal right here. We don't close it, because if you close it, the connection will just the connection process will be killed. So we use a new terminal, and we type this ROS launch to move it .launch, and this will just bring our move it here. And because now your robot is sending its joint status to your ROS, so you can see ROS here already generated your robot in Arvis, and this status should be completely the same as your real robot. Now you need to add a panel designed by our R&D. Click Add New Panel in your Arvis and select this Drupal control and hit OK. You will see a new control panel over here, and you can use this panel to enable your robot like in our other softwares. And now the robot is enabled. You can see there is a little movement on the robot, and this connected state is connected, and your robot is ready to move. And now we drag this end effector to somewhere else, as we did in the virtual space. Now it's in the real robot. So drag the end effector to your target point, and hit plan and check if the move is okay. Then we hit execute. Now the robot will just move to the orange point, to the orange one. So there's some lag in the screen recording, but the simulation in the RVS and in the real world should be synchronized. Okay, so the last part will be some custom function development. Because you need to know how everything works, you cannot just use move it to do everything. So basically, all the robot functions like enable robots, disable robots, move L, move J are all defined as a service. So you can find all of them right here. Catkin workspace, source, our package CR ROS, or if you're using MG Pro or MG400, your package, and Drupal bring up services, you'll find all the commands right here. And you can use them with, I will show you in the terminal, okay? Yeah, you can also check them, all the raw service with this command, raw service list, when your robot is connected to your PC, okay? And it will just list all the commands that you can use, and you can check it out. All right, so now let's do a simple thing. We enable the robot. We use raw service call, and we find this command, this service right here, Drupal bring up service enable robot. You can see the robot is enabled, and the return value is 0, which means there's no error or warnings. And the TCP just received this command, which is enable robot. Okay, so the next example is to move the robots. Okay, the command now is joint move J, and we type in all the parameters that we need. And hit go. We will just do as everything you instructed. And you can see all the commands are sent via TCP, and this is what the robot actually received. And the return value is 0, which means still no error, which is a good thing. And joint move J, this is the joint coordinate that we sent. Okay, so basically this is all for our today's training session. If you have any questions, you can ask them right now.
Hi, Gary here. I'm not one of the programs, I'm on the sales side of things, but in talking with the guys that have been working here, when an error comes up, does it tell you what the error is and where the error is? Or my understanding is it's a bit of a search to find where the error is.
Yeah, we have a TCP IP user guide, and we list all the error codes inside it. Like if there is a -1, which what's the meaning of the -1, which is the meaning of 10,000, what is the meaning of 40,000, something like that. I will send it in the chat, okay? And you can check it out.
Yeah, we're gonna send you the GitHub link.
Yeah. And yeah, you can
Thank
find
you.
all instructions in the README file in our GitHub package. So all today's commands will be listed in the README file. I'll try if I can find it right now.
Okay, thank you.
Screen. Okay. All right. Yeah, right here. Yeah, this TCP IP protocol, which is basically what is being used when your computer is communicating with robots. So you can see this README file. Right here. Oh, sorry.
Something that we gotta make sure that click on English.
Yeah, the English version.
And you can search for error code. Error.
Should be error code description. Yeah, right here. So we just saw that 0 means no error, and if you receive these error codes, you know where to find. All right. And
Good question. And any question, feel free to turn on your mic.
yeah, just feel free to ask any questions. I will show you. We have this. Yeah, CROS, which is I just used, and you can see there's a. I'm sorry. README file. Yeah, this is the README file is not up to date. It's still telling you to install Ubuntu 16.04 or 18.04. But 18.04 is let's say 18.04 is more stable. 18.04 was released like 3 or 4 years ago, and for these years is always being tested by all engineers, and that's what I learned when I'm in college. So 18.04 is I'd say that's a stable one, but it will be end of life in May 2023. So I'd recommend you to move on to the new version 20.04 and the new version of ROS Noetic. So you can basically see all the commands that I demonstrated in the video today, and all the movie control, everything. So just check our GitHub. All right. So any more questions? So if there's no question, we can take a break and we will move on to the next part in like 5 minutes or 10 minutes. All right. Any more questions for now for the first part about ROS? All right, great. So that I assume there's no more questions for me. Okay, so now let's take a little break, and my colleague will introduce about palletizing, things like that later. Okay. See you in a few minutes. Guys, come back in 5 minutes, and we will move on to the next one. Okay. See you later.
Okay, so I am going to go into the process of palette. Okay, I'm going to talk about this, and it's pretty simple for using our graphing our graphing programming. I am going to show you a video I just made a few days ago. Okay. Let me know if you can see it. I think you might. Okay. I think all good, right? Okay, let me keep doing that. So what I am doing is I want to do pilotizing using our graphing programming. I use this MG400 as a demo because it's smaller, but you can use it on a bigger robot. The first thing is you go to Dubo Studio and click on the Blockly, which is our graphing studio, graphing programming windows. And this is our demo. We are going to share to you, or we are going to share the PPT anyway, and also the recording of the meeting. And this is my simple code. Let me explain it to you. First is move J to 0.5. I have a 0.1 to 0.6, right? 0.5 is a safe position. It's not going to knock down anywhere. It's up high, right? So if go to different, it's easier to go to different place. So this is the 0.5 I set up. And then I use our command is called pilot start position. And on this, it's going to set up the equation. And you want to, after you pick up the place, you want to put it 2x3 or 3x3 or 4x4x4 and whatever you want. So this is, I'm going to get into the setup on this command soon. And then after I set this up, I need to tell the robot to turn off the suction cup. Make sure the suction cup is off first, and then turn it on, and then pick it up apart and drop it off. After it drop off, I turn off the pump and turn on the air. Turn on the air to push out the part a little bit, and then repeat. So repeat to a safe point, which is P5. So this is going to repeat, and the video is going to show you. And I apologize that I dragged the camera around on the window. It's kind of blocking the wheel sometimes. Okay, and now I'm showing that to set up all the points, we have a 0.5, which is the safe point. It's up high. It's not going to block anything. And we're going to set up 0.6. Okay, this is 0.5. And I'm going to set up 0.6. 0.6 is where we pick up the object, which is here. Here is 0.6. I need to preset them. So I'm going to go to P. Okay, I'm going to click run to. See, when you click run to, you can click run to check if it's the location that you like. So I just click run to, and then it go to a pickup point. So I know that this point is good. Okay, then I know it's good. Adjusting, just make sure it's in the center. Okay, and then now I need to go to set up 0.1 to 0.4. Okay, this is the setting of our palletizing graphing user interface. So I can either pick 2-dimension or 3-dimension. 2-dimension is mean we only put on one layer, right? So it's going to be 3x3x1. It's just one layer. But also we can set up 3-dimension, which is you can stack up together, 1 layer, 2 layer, 3 layer. The setting is a little bit different, and we can change the setting by here. Okay, and now I'm saying that for this, where is the 0.1 to 0.4? Is here. Here it start at 0.1. This is going to be 0.1, and this is going to be 0.2, and this is along the x direction. You can see along the x direction. 0.1 to 0.2 is x direction. 0.1 to 0.4 is y direction. So I need to set them up. And for this demo is 2x3. And high offset is, you don't need to put in anything because I only have one layer for this demo. So this is 2x3. Okay. And okay, when you click on here, oops, too fast. When you click on pilot dimension, just a second. Okay, pilot dimension. You have 1 dimension, 2 dimension, 3 dimension. 3 dimension is stack them up. So I'm click on it. So, okay, this is 3 dimension. If you want to stack them up, you need to also tell them the Z position. So you're gonna tell the Z position. So the high offset is going to be important. And you're gonna set up the number of Z direction. So if you put 10 there, it means you're gonna stack up like 10 layer. So it's going to be a 2x3x10 layer. Okay. And because I only have 6 different cylinder block, so I am going to show you this 2 dimension. Now I need to set up 0.1 to 0.4. What I do is I drag the arm. For CR is the same. Drag the arm, and it's better to use a point and effector to point out the center. That is really important. I can click cover. If you don't have the P1s already, you click add. If you already have it, you click cover to cover XYZ. So now I move to 0.2. And then the cover, that's the X direction. And then I'm going to move to 0.3, which is the diagonal position. And I'm going to cover all the point. And then go to 0.4. Okay. After that, I go. Oh, also there's an advanced setting. You can change the speed and acceleration. Okay. After all that, it's pretty much good to go. For DO, the digital output, 10 is mean the pump to suck up air. 11 is to push air. So I just need to make sure when it grab it, it suck up the air. When it drop, it blow the air out. So make sure that this is gonna be. I put delay there, so it gotta push the air a little bit longer. You know, for 0.4 seconds. Make sure it drop. And that's pretty much all the setup for palletizing using our graphing programming, Berkeley. Okay, now it's, oh, sorry, I pull out it too hard. I'm going to clean the alarm. I'm going to clean the alarm and do it again. Okay, good. Now it's good to run it. I'm going to run it. Save it. And it's good to run it in really low speed at the first time. And also because our tool is offset, so I have tool flame, which is number 3. Okay. Now let's take a look. Okay. Now it go to 0.5 at a safe point, and then now go to P6, which is where to pick up the object. Okay, and then jump out at the first location. I'm gonna pick it up again, and jump to the second destination. Okay, and then I'm gonna pick up third one and drop it to third location. Then I'm gonna pick up again. And then I'm gonna do it again. Yep, and that is how we do palletizing on our graphing programming. It is pretty easy. Yep, it's pretty easy. And I'm gonna stop sharing a little bit. I'm gonna take a screenshot just for my record. Okay, and then we're gonna start sharing screen. Okay, and that is wait a second. Okay, so this is how we done. I just show you the video, so I need to just go over this. Okay, and if you want to do it on the script, you want to type, you are a traditional programmer, and this is how you do it. And we have a demo code. First, always good to set our home point, which is the safe point. Oops. And then the point 2 is the first point to pick up. And then we want to offset, right? Each time you drop off an object, you want to offset by the side. And so I want to, on the X direction, I want to offset 50. Y direction, I want to offset 100. For Z direction, offset for 50. So it's the height of the object. And then I have an algorithm for this. Each new coordinate is going to be the old coordinate plus the offset X on X direction, Y direction, and Z direction. So each destination is going to be offset from a previous location. So it's going to be changed each time, each location when you jump. So, and this is it. This is really short code. And also when it's going to count, right? It's going to be counting. If it's 3 by 4, it's going to count it 1, 2, 3, and then go to last line. It's going to start over again, 1, 2, 3. So it's going to count it to 3, up to 3, and if it's 3, it's reset it to 0. So this is the process of palletizing. Any question? Feel free to turn on your mic and ask me any question about palletizing.
Hi, Gary here again. So basically this program, we are doing something that is opposite. We're taking off a pallet and putting it on a conveyor. So we could still use this software just in reverse, right?
Oh, yes, definitely. So we have another block is doing the opposite direction. Take it off from this place, yeah, to stack them together. And if you use 2 together, it's going to be, yeah.
Yep. Okay. No, we have an end of arm effector that's picking up 5 pieces at one time and then putting it on there. So no, this is great. Thank you.
Yeah, good, good. Are you using what kind of programming you use most likely or more often?
As I mentioned before, I'm on the sales side of it, so I'd have to bring one of the techs that's programming, but they're busy at the moment, so
Yeah,
I
yeah.
can't answer that at the moment.
Yeah,
Sorry.
yeah. It's all good. It's all good. It's all good. So any other people have question? If no, then I am going to go to a next one. Next one is going to be process of Vision Pilot. Let me stop my screen. Pull it out. Gonna pull it out. Okay. Okay. So for some reason, when we play a video, the other side does not hear anything. So I'm gonna mute it, and I'm going to just talk along. So we have, oh, we actually have it somewhere here. Let me show you. So we can do a palletizing using a camera too. So the camera can tell where to pick up the object. So we have, this is our end effector. It's a suction cup. It's a really small, tiny one. And also it's offset. So when we use it, make sure to set up at the correct tool coordinate. Set up the correct tool coordinate. So we assemble it, we put it there. After we secure it, we have to, oh, this is the tool for air, for compression air. Okay, so now we can get set up the two center point, TCP. It's really easy. We go to menu and then go to setting, coordinate system, tool frame, and all you need to do is click anyone and modify it, and it only requires 2 points. So we stick a needle there. So point to point, and then we click on the first point, and then we mark it. So, or we just fine tune it. Change the pose of the tool. Okay, and then drag it somewhere, and then point it to the same point again. So on the 2-dimension, tool line can identify the 1 point, right? Any tool line, as long as not parallel. Okay, now we put calibration board. I mean, you can just draw anything. We only need 4 points. The purpose of this is to match the camera coordinate system to our robot system. So any given point can match the on camera, also on the robot. You on the setting, we gotta pick software trigger. We click once and then take a picture. After we take a picture, we can find 4 points on the picture. You see that? We select them. We select 4 points. So now we have 4 points. The camera know 4 points. Now it's the time to drag the arm to point it to these 4 points. So 2 coordinate system match together. So After it did that, it generate 4.0123. And then we go to select script vision palletizing. Okay, now we have to point it out to point A first, point A. Point B, point C. This is 4-point calibration. We have 9-point calibration. 9-point is more accurate, but lot more point to do. Okay, after that, you generate a calibration file. And that's how two coordinate match together. Now we can switch to the real software and load up the calibrations module that we did. And for this, let me show you this. This is to, whenever you want to recognize whatever object you want to recognize, first thing you do is take a picture using our vision system, and then let the camera to learn what is this part looks like. Okay, you see that? After we took a picture, it know the edge. If the edge is matching this part, then we know it's good. And we do go to a calibrating module and then turn on TCP. So a lot of people ask us what kind of camera is suitable for our robot. The answer is whatever camera that support TCP communication can work with our robot. Actually, our robot does not even know if this is a camera or this is a computer or what. We don't know. The robot only read data from TCP. So the job for vision system is to generate a correct coordinate and send through TCP to our robot. So my robot know where to go. So any camera that work with TCP communication can work with our is suitable for our robot. So now I just set up the IP address. Okay, after we have our IP address, now we can run it. Okay. So, okay, grab it. Oh, this is still calibrating. We need to calibrate where to drop off. Okay. Pick up, drop off. Okay, pick it up and drop it off. So actually you can run this without the camera, but if without the camera, you have to make sure this is always in the same direction that you set up. But with the camera, any rotation here, if it's off by 20 degree, 30 degree, whatever degree, our vision system can recognize it and rotate and place to the correct position to drop up to a correct position. But we know that a lot of industry don't use a vision system. because they can make sure, on the production line, all the product come out equally, no rotate. Okay, so this, let me make it small. This is the vision for pilot. Okay, any question?
So I know you're using your smaller robot, but just reconfirming that all of the programs that we're seeing here and the demonstrations that you're doing can easily be applied to any of the CR family, correct?
Yes, actually, I have one is exactly the same, but with a CR. With all of them like that. This is our training studio. So let me show you. This is the one that with CR. Its setup is exactly same as the video that I showed, and that one is with MG400. Oops. Bring out to here. Setup's the same, but with a different robot.
Okay.
Yep. Wait a second. Oops. Oops. Wait. Where's my mouse? Okay, back. Yeah, it just when we do demo, we use a smaller robot at now, but I think later on we're gonna have all the demo. Not demo, I mean video report. The user interface software, everything is same. And the PPT, it just goes through the video that I taught. First set up the two frame. Two frame only require 2 points, and the more precise way is point to point, needle to needle. And that's the software you need to set up, the how to trigger it, and the lighting and 4-point calibration to match the robot coordinate to the vision coordinate. And after that, generate a platform calibration module, and then take a picture of the object that you want to move, that you want to pick up, that you need to recognize it. And for this case, is this thing. This is, I would say, rectangle, but not exactly. And then set up the IP of the camera, and then you need a script. We have this demo also, and yeah, and start running. We have IO for this. I don't think you need this. If you purchase you already have our training station as shown on the video, and this is all the wire hooked up. So digital input is start, digital input number 3 is stop, and this is all the description of all the IO in and out, in and out, in and out hamburger. I missed that. Yeah, that's just the demo script. So any question on this? Any question? I'm going to stand here and wait for anyone. If anyone have question. If not, I'm going to still be here and then taking a break for 5 minutes. And then after that, we're going to continue for next
Hey, Joe, this
So
is
yeah, I
Mauricio.
do have a question. So, we're, new to DoBot learning and doing different applications. And I'm seeing that there's a number of tools in here that our guys, I'm assuming know, or maybe are not aware of all of them. So I'm just thinking out loud that depending on some of the new applications that we are doing, maybe I should send that through to Luna, who's our sales rep, and say, this is an application we're quoting on. And then you and the tech team can say, here's some tools to help program that application. Just to make sure that we haven't missed any of these nice tools that are available.
When you say tool, what do you mean by tool? What kind of tool?
What I mean is, like, you have already a pre-programmed system for palletizing, as an example.
Yes.
That's a great tool. Depending on what I'm doing, you may have other examples of that is easy to use to facilitate the action that we're looking to do.
Yes.
So I think what I'm saying is, we're going to communicate a little more through Luna, some of our applications, so that we can do some of these a little faster and use all the tools that you have available for us.
Yes. And I just sent out our email address. It's for technical support for American region. And you can ask any question over there. For now, we have pretty good demo script, programming script video on this training station right here. This training station.
Okay.
Pretty good. We have few demo, and it show you how to work with camera, how to work with the conveyor belt, how to work with the what else? Palletizing. Yeah.
And our guys have been communicating with you. And again, I'm more from the sales side, so I don't know how much they are, but I'm certainly seeing a lot of good tools that we can use.
Yeah. Yes. Just email us whatever you need. Email us. We're gonna help you with that. And also, you can CC Luna. Okay.
Great.
I hear some other people have question too. All right, feel free to turn on your mic.
Can you hear me?
Yes.
This is Mauricio Rives in Chile. Yeah, I'm just looking at your equipment as an alternative for us, and it's interesting. What I've seen is that you can do positioning, picking, and making palletizing or something like that with objects which are more or less the same, very accurately, because you're placing them and picking them up from very accurately known locations. Is there any way you can be a little more tolerant, like, for example, picking up a slightly different object, like for example, a fruit, like an apple?
Oh, okay. If fruit and apple, then is the critical part is the gripper that you're gonna use, or suction cup. That I think that is the critical part. I don't know how you're gonna grab it.
Okay.
Okay.
If we have solved that problem, can you adjust it maybe 5 millimeters the position depending on the size of the object?
Adjust on where? On the end effector, on the vision system.
It would be probably on the height, the Z-axis. Yeah, you would need to maybe adjust lowering the arm plus minus 5 millimeters.
What do you mean by lowering the arm? Sorry, I don't quite get it.
When you pick up
I have one here, and what do you mean by lowering the?
When you go to the origin of the pickup point, yeah, your Z-axis, your Z coordinate is fixed. Yeah, well, all three coordinates are fixed, but assume that the size of the object can vary in maybe a few millimeters. Can you adapt for that somehow?
Are you saying that you want to move this to lower?
Yes.
Oh yes, yes. Of course, you can make it much lower. You can, you see that the joint here?
No, excuse me, not not lower every time, lower according to the size of the object you're going to pick up. Yeah,
Okay,
your pickup object is not the same every time. There's a variation
I see.
in the size.
I see. I got what you mean. Okay, I think there's two solutions.
Okay.
One is you use 3D vision, so you know how deep you're gonna go.
Okay, got it. I understand. Fine.
Okay.
No more. I can follow on that.
Yeah. Second solution is what we see a lot on CNC is the gripper have a spring on it. So if have a spring on it, so if it touching here, actually it can compress. The gripper
Okay.
compress a little bit, so it's not gonna be a hard hit. Yeah, it's gonna.
I understand. Okay, both solutions are possible. Okay, that was it for the moment. Thank you very much.
Oh, you're welcome. You're welcome. Work with 2 camera. Okay, can the CR robot work with 2 camera? Okay, the thing is, all our robot doesn't matter work with how many camera. So the only thing is the camera sending a signal through TCP to our robot. So it can work with as much as camera you like. Okay, so for this demo, actually using 2 systems. Let me show you 2 systems. One is the vision system. Vision system is using to take picture and generate data, normally X, Y, Z, and then to send it to our robot controller. Our robot controller will read the data. So if the vision system is it can support 2 camera, 5 camera, 10 camera, then our robot is fine to receive the data from the vision system. So actually, it's, yeah, good. So it does not matter. And we have demo to work with 2 camera. I mean, it can work with more than 2. It does not really matter then, yeah. Okay, I'm glad that I answered your question. Any more question? Okay. If there's no, I'm gonna stand here for like a 10-minute break. I'm right here. Any people have question, feel free to turn on your mic. Yep.
Hello guys. Can you hear me?
Please share your screen. Jixiang, please share your screen. Yep, good.
Oh, hi everyone. Can you hear me? Okay, I'm Jishan and I'm going to bring you the next training sessions, which is about the dynamic piloting. So we also have a video that's you can refer to if you are using the MG400 training systems. So today's training will based on the videos. We have introduced you the piloting and the vision system. So in this application, we're combining the conveyor into the system to do the dynamic piloting, which means that dynamic piloting means that the object will move along the conveyor and the robot will tracking the object and pick it in the process and move it to another place for the pilots. So this is the process of how to accomplish the piloting program. First, the first two steps is the same with the vision. Is the vision piloting. Is to install the eccentric tools and establish the tool coordinate systems. I think you already learned about that. So we'll skip the first two steps. And then we'll move to the step 3, establish the user frame. Because we are using the dynamic tracking. Aside that, we need to establish the tool coordinate system. We also need to establish a user coordinate system, which the x-axis is the same as the conveyor movement direction. It is for the robot to track the object. So we need to create a coordinate system. And we can accomplish that by using the 2-point calibration methods. The step is almost the same. We go to the settings and the coordinate system, find the user frame, and you can see that we have like total 10 user frame you can customize. Oh no, it's 9. We have 9 user frame you can customize and 1 default user frame that you cannot modify it. So you can choose number 1 to number 9 to pick one and user frame to modify them. So in this case is the user frame 1 and select the 2-point settings. And the method is slightly different. So we point the needles to the calibration tools and obtain the coordinates of the first point. You can see that from the videos. And you should remember that all the calibration process is done using the tool frame we have just created before. And then we'll have to move the conveyor. Move the conveyor a little bit so that the calibration tools will move along the conveyor like 10 or 20 centimeters. If you are using the MG400 training station, the corresponding digital output is digital output 4. So you just turn on the digital output 4 and the conveyor will move it. And like we'll stop it here. And then we'll jog the MG400 to make the needle points to the calibration tools. and then we'll save the acquire this point as point 2 and click the OK. So we are successfully create a new user frame. The next step is that we'll configure the piloting and the conveyor. Because we are combining the vision system, so we also need the calibration papers to do the to combining the pixel coordinates of the camera and the collision coordinate system of the robots so that we can match them and the robots will know where to will know the exact coordinates of the image. So we attach the calibration papers to the conveyor, and we move it under the camera, and we need to use the Robot Vision Studios, and we will gonna create a calibration progress. I will choose the corresponding camera and we'll take a picture. Then we'll make a tablet out of the cross. Make a template, and we'll have to record the pixel. We have to record the image position of each of the 9 points. It goes by a certain orders, like they're from 1, 2, 3 to 9. After that, we're gonna to import the demos we have right on the of the dynamic piloting, and we'll select the process to configure the conveyor parameters. So we open this interface. We have to choose the conveyor index. So in this case, it's 1, and we also need to choose the user coordinates. So in this case, we just create the coordinate system 1. So we choose coordinate system 1. And we are combining the vision system. So we'll choose the data source as camera. And the next step is that we are going to calibration the resolution of the encoder. The process is almost the same as the process we calibrate the user coordinates. So we get point 1 here, and we move along the conveyor to another point and jog the robot to so that the needle points to the calibration tools, and we get the coordinates and the encoder information of this position, and we click calculation to get the resolution. So the next step is that using the to match the camera image position to the actual position of the robot. So this is a basic camera parameters we need to modify. The width and the height should be the same as the camera you're using, and the digital outputs should be in our case we can use the digital output 12 to trigger the camera to take pictures. So we select the digital output to 12, and we'll modify the interval and the repeat threshold.
Utiliza las teclas Control H para visualizar los archivos ocultos. Primero es necesario configurar algunos repositorios de Ubuntu.
After we finish the basic configurations of the camera, we'll have to match the position of the camera and the robots. So you know that we take a picture and record the 9 points, the image position of the 9 points, and we will input them by the orders. And before you do that, you need to click the conveyor position to get the current conveyor positions. And after we done like transfer the data, we need to click the next. So we need to input the actual position of the robots. The first is that we'll need to move the calibration papers to the work range of the robots. And then we will click the conveyor position to record the current conveyor positions. And we need to run the same orders, like from point 1 to point 9, and to input the coordinate information of the robots. In this case, we don't have to like to type the actual coordinates. We just click the 1, 2, 3, 4, and the coordinates will shows. And after we done that, the robots will after we have done that, and the camera will send the image information to the robots, and the robots will calculate the actual position where it will go. So the next step is to determine the working space of the robots. So we need to define working upstream limits, the working downstream limits, and the pickup downstream limits. So the working upstream and the downstream is where the robot will tracking the object, and the pickup downstream limits is that the robot will pick up the object before the downstream limits. And after that, we have successfully configured the conveyor parameters. And the next step is that we are going to teach 6 points in order to run this program. So you may remember that we have create a user frame 1. So the P2, P3, and P4 is taught in user frame and the tool frame 1. And the other 3 points is taught using user and tool frame 0. In this case, firstly, we need to taught the like the Z coordinates of the P2, P3, and P4, and taught the P5, the transition point, and the P6 is the first point of the placing. Then we have to configure the camera, the dynamic piloting program. So the the progress that is that the camera will take a picture. If the robot sends the digital output 12, the camera will take picture, and if it matches the object, it will send the image data to the robots. And we are using the robot as a server and the camera as a TCP client. So it will connect to the robots through the 8080 ports to send the data to the robots. And then this is the actual progress the robot. So when it reaches the photo area, the camera will take a photo and send the data to the robots. Then the robot will know where the object is, and it will move. It will move along the conveyor to track the object and pick it up, then and do the palletizing to place it in different place. So this is the main parts of the dynamic piloting, and here is the PowerPoint of this progress, and it's I think it is more it introduces more about which how to configure it, all the parameters, and what is they stand for, and how to modify them according to your situations. And here is some commands we are gonna use when we use the conveyor applications. So this is about the dynamic piloting program. So do you have any questions? Hi everyone. Yes, the Duba version studio will recognize the color image. For example, if you are choosing, I think I'm sharing screen now, so you can see the modification I'm doing here. So if I choosing if I choosing the pixel format to RPG24, and then the picture will be sorry. The picture will be color pictures. So, and it also can distinguish the whether it's like red or blue or other colors. Okay, thank you. And do you have any more questions? Not just about the progress, not just about the dynamic piloting, like any questions concerning like using our product? So we'll have to wait here for another 10 minutes. If you have any questions, you can just type it or ask us.